In this DeBacco University video, I'm going to be taking this flowchart and describing it in more detail. So by the end, you'll understand how you go about naming ionic compounds. All right, when you write an ionic formula, you may have heard the crisscross method. And this is very important for transition metals because you want to start by looking at the formula and charge of its partner to determine what the charge is of that transition metal. So in this example, we know oxygen has a -2 charge, and we see a 2 as a subscript below the iron. So the question is, what is the charge of this transition metal iron? So when we do the reverse crisscross method, here we're looking at here, this would indicate that iron in this example has a charge of 3. In this case, it'd be a +3 because oxygen has the -2. And that's how we get the Fe2O3 formula writing. So how to go about naming these compounds? Well, we first want to identify the ionic compound, whether it's a binary ionic compound, meaning it's made of one metal, cation, and one nonmetal would be the anion. Essentially, that'd be 2 ions, as we can see some examples over here depicted. Or we could have a polyatomic ion compound, as this includes one or more polyatomic ions, which are many atoms that interact as if they were just a single ion. So how do you go about naming? Well, step 2 of the naming, get ready to refresh yourself with Roman numerals. If it's a metal with a fixed charge, like a sodium and a calcium, you simply just use the element's name. So Na+, simply just sodium. However, it's a metal, particularly a transition metal with variable charges like iron, could be Fe+2 or +3. You want to use Roman numerals to indicate the charge. So here's our example. Fe2 would be iron 2 with the Roman numeral, and 3 would be the iron with Roman numeral 3. So refresh yourselves with these, particularly 1 through 10. Then you want to name the anion, which as a reminder is the negative ion second. For monoatomic ions, a single element, then the change in the ending to "ide." So instead of chlorine, we'd have chloride. Instead of oxygen, we'd have oxide. So you name of the cation metal and the base of the anion, which would be the nonmetal plus "ide." Now for polyatomic ions, we use the standard name. So hopefully you're starting to see as this indicates kind of this building of, we start with the cation, do we just do the element name or do we use Roman numerals if there's a possible change in charges? For our anion here, it ends in "ide" if it's a binary compound, or we simply use the ion name if it's polyatomic. Then we simply just combine the names. So cation named first, followed by the anion. So NaCl would be sodium chloride, FeCl3, iron 3 chloride, CaSO4, calcium sulfate, because SO4 is a polyatomic ion. So you can kind of see how all these individual components are all coming together to generate the name of these ionic compounds. Now there are some special cases that I do want to highlight, one of them being hydroxide compounds or bases. This includes the OH- as the anion. So NaOH, very common one you might work with, sodium hydroxide, CaOH2, calcium hydroxide, and then ammonium hydroxide. So again, we're looking here at the naming of the bases. The OH indicates a hydroxide. That is kind of, I put it at the end there because it's the anion in these examples. We also have ammonia compounds. So Na+4 is ammonium. It's a polyatomic cation. So NH4Cl would be ammonium chloride. So ammonium is a common ion with a +1 charge. Sulfate is a common ion with a -2 charge. So we always remove the word ion. So we just get ammonium instead of ammonium ion and sulfate ion. We just would get the naming as ammonium sulfate. We could see here, because of the difference in charges, we put parentheses around those polyatomic ions and put the number there as a little subscript so we can indicate how many of each of those polyatomic ions are present. Then we have hydrates. So our last kind of special case we'll talk about in this video will be hydrates. And you're adding a prefix for the number of water molecules. So CuSO4 times 5H2O would read as copper 2 sulfate pentahydrate. So its copper is a transition metal, so we have to indicate its charge with the Roman numerals. Sulfate's a polyatomic ion with known standard charge. And then we have 5 water molecules. So our prefixes come back into play. We're looking at pentahydrate. We're looking at di if it was 2, hex if it was 6, so on and so forth. So again, all of the naming follows these same basic rules. Applying it to different examples will allow you to become increasingly comfortable with all these little nuances so you can write proper ionic formulas.